promised, we're back with more on sequences and series, this time diving into geometric sequences and series. I had briefly mentioned these at the end of my video on arithmetic sequences and series. Remember, arithmetic sequences and series, you added something to get to the next term in the sequence. You had that common difference, that fixed constant common difference. This time with geometric sequences and series, though, we're worrying about multiplying. In fact, by definition, a geometric sequence, so we'll focus on the sequence first, series later, also called a geometric progression, is a sequence in which each term after the first is obtained by multiplying the preceding term by a fixed non-zero real number. Called the common ratio. So earlier with arithmetic sequences and series, we had the common difference. This time we have the common ratio. Okay, for example, let's say you have the sequence 1, 3, 9, 27, etc. Okay, this is a geometric sequence. If you take 1, you can multiply by 3 and get the next term, 3. If you take 3, multiply by 3, you get the next term, 9. If you take 9, multiply by 3, you get the next term, 27, etc. So a common ratio here is the 3. That's what you're multiplying by. So the first term was 1. A sub 1 is 1. Common ratio is 3. Now, if you want to think about this in more generic terms, you can take whatever a sub n is, like some term in the sequence, times by that common ratio, and that'll give you the next term, a sub n plus 1. Or you can rearrange things and say that the common ratio is a sub n plus 1 over a sub n. Like if you wanted to find your common ratio, you could take from, like, for example, from this sequence, 1, 3, 9, 27, etc., you could take two consecutive terms, and you can divide the one on the right by the one on the left, and that'll give you the common ratio. Like if you did 3 and 9, you could do 9 divided by 3. That gives you 3. Or you could do 27 divided by 9. That gives you 3. So that's what that definition is basically saying. So you could take any term after the first and divide it by the preceding term, and that would be your common ratio. Now, if you think about this a little bit further, okay, so you have 1. Then 3 is 1 times 3. 9 is 3 times 3, which is the same thing as 1 times 3 times 3. 27 is 9 times 3, which is the same thing as 1 times 3 times 3 times 3, etc. So if you look at the way that's going, look at that common ratio and see how many times you're multiplying by it. you could come up with a statement for A sub n. You could say, well, A sub n is the same thing as A sub 1 times whatever that common ratio is, raised to a power that's 1 less than n. So like A sub 4, you're taking A sub 1, which is 1, timesing by the common ratio of 3, raised to a power that's 1 less than 4, which is 3. So that gives you a nice little, so A sub 1 is that first term. R is that common ratio. And we have n for the nth term. Okay. So let's look at an example or two dealing with, these geometric sequences and common ratios. Let's say that a person receives a gift on the first day of each month for a year. So they start with $50 on January 1st. And then the amount doubles each month. So how much is received on December 1st? Okay, you could sit there and try to figure it out. You could say, well, January 1st is $50. So then that doubles on February 1st, you get $100. Then on March 1st, you get $200. It keeps doubling. Each month, whatever the amount was previous month, it doubles. So but we can, instead of actually sitting there and working all that out to December 1st, keep in mind that doubling means you're multiplying by 2 each time. So you're dealing with 2 to some power. Your initial amount was $50. That's your A sub 1. So you can figure this out. You could say, well, December will be A sub 12 because there's 12 months in a year. January would be the first month. December is the 12th month. December would be A sub 12. And you could take the A sub 1, which times r to the 12 minus 1 and figure this out. So we're trying to find A sub 12. So you're going to take $50. And then the r is 2 because you're doubling it each time. You're timesing by 2 each month. And that's going to be raised to the 11th power. So let me see here. Let me put that in my calculator real quickly. And then figure out what that comes out to. All right, if I do 2 to the 11th power, I get 2,048. So I'm going to have $50 times 2,048. And when I do that, I get $102,400. Because, we're starting with $50 the first month, but we're not doubling it yet. We start doubling it the second month. So it's only for 11 months that we actually do the doubling. So that's why 2 is only raised to the 11th power and not the 12th power. And then, but, you initially started with $50 and you times by 2 to get the next second month. Then you times by 2 again to get the third month. Then you times by 2 again to get the fourth month, and so on. So you end up timesing by 2 11 times in order to see what you get on the 12th month. All right, let's look at another example. Let's say you have the geometric sequence 6,400, 1,600, 400, 100, etc. Okay, and they want you to find a sub 5 and a sub n. If you look at it, you can kind of tell what's going on there and get a sub 5 pretty quickly. To go from 6400 to 1600, you can divide by 4. To go from 1600 to 400, you can divide by 4. To go from 400 to 100, you can divide by 4. Or you can do the whole thing of, you could put, like, in order to find that common ratio, you could put 1600 over 6400. And you get 1/4 common ratio. Or if you did 400 over 1600 or 100 over 400, all those would give you the same common ratio. So to get a sub 5, one way to do that would just be to take 100 times 1/4, and you get 25. And then to get a sub n, use your formula. A sub 1 times r to the n minus 1. So a sub n would be 6400. That's the first term in this sequence. And then our ratio is 1/4. And then that's raised to the n minus 1. Which if you wanted to, if you want to find a sub 5 this way, you could do 6400 times 1/4 to the 5 minus 1. And you would still get 25 if you did it that way. Because you're taking 6400 and timesing by 1/4 4 times to get there. All right, another example. Let's say you have a geometric sequence where a sub 2 is negative 18, a sub 5 is 486, and you're trying to find r in a sub 1. So remember, with geometric sequence, you're multiplying by something to get from negative 18 to 486 there. So what I'm going to do is I'm going to divide 486 by negative 18 and see what that gets me. But keep in mind that's the fifth term divided by the second term. And that'll help me to think about what's going on here. I get negative 27. So essentially, to get from negative 18 to 46, I have to multiply by negative 27. Because you can do, if you do negative 18 times negative 27, you get 486. But there's a lot going on in between with a sub 3, a sub 4, in between there. So there's actually 3 multiplications that would have to happen to get from a sub 2 to a sub 5. So there's a multiplication from a sub 2 to a sub 3, from a sub 3 to a sub 4, from a sub 4 to a sub 5. And so if you're multiplying and getting negative 27, multiply by negative 27, but you have to break that up. You have to think, basically, what's the cube root of negative 27? And that would be negative 3. Negative 3 times negative 3 times negative 3 is negative 27. So that tells me my common ratio. Tells me that's negative 3. So another way to think about that is I could a2 to a5, I could subtract 5 minus 2, I get 3. And then just take the cube root of whatever it was that was multiplied to jump from one to the other. So then they wanted a sub 1. Oh, well, if you know a sub 2 is negative 18, then a sub 1 can be negative 18 divided by negative 3. Because you're going that other direction. So you get 6. That's one way to think about that. All right, let's think about a word problem, and then we'll get to geometric series. Population of fruit flies. I'm currently reading a genetics textbook, and they do love to use fruit flies in their experiments. Population of fruit flies is growing in a way that each generation is 1.75 times as large as the last generation. So 250 insects in the first generation. How many in the sixth generation? It says round to nearest whole number. Okay, so it's growing so that each generation is 1.75 times as large as the last. 250 insects in first gen. All right, so A sub 1 is 250. Now we could sit here and we could go, well, let's take 250 and then multiply it by 1.75 to get second generation, by 1.75 again to get third generation, 1.75 to get fourth, 1.75 to get fifth, 1.75 to get sixth. Or we could recognize that 1.75 is our common ratio here, because we're starting with an initial amount of 250 for first gen, and then multiplying by 1.75 over and over again to get, more generations, to get the populations. And in this case, trying to find out about the sixth generation, so n is 6. So you can say, well, A sub 6 equals 250 times 1.75 to the 6 minus 1. So 250 times 1.75 to the 5th power. All right, so I'm going to put that in my calculator. 1.75 to the 5th power is this crazy decimal, like 16.413, blah, blah, blah. I'll go ahead and write it down in case you're wondering. That's where my calculator stops. And I don't round, I just go ahead and hit times 250. And I get 4103.271484. They asked me to round to the nearest whole number. So this will round to 4,103 insects, fruit flies, in that sixth generation. So there you have it. Okay, now as promised, we're going to get into series next. So we're going to jump, just like we did with arithmetic sequences and series, we're going to jump from geometric sequences to geometric series. And it's the same kind of thinking where if you know the terms in the sequence, you add them up for the series. So geometric series is the sum of the terms of a geometric sequence. And just as you might suspect, there is a formula. So let's figure out what that formula would be. So the sum of the terms could be written as a sub 1 plus a sub 2 plus a sub 3, etc., all the way to a sub n. So right now we're just dealing with finite. We'll deal with infinite later, so we will deal with it too. But this could also be written, since we're talking geometric, as a sub 1 plus a sub 1 times r plus a sub 1 times r squared, etc., until you get to a sub 1 times r to the n minus 1. It's based on what's happening with the geometric sequence. The first term's A1, second term takes that times r. Third term takes that times r again, and so on. So the number of r's you're multiplying by is one less than whatever term number you're dealing with. Now we can work with this a little bit. If r is 1, it's not very exciting, because then your s sub n, you end up with a1 plus a1 plus a1, you know, n times. So you end up with n times a sub 1. But what if r is not equal to 1? Then we can multiply both sides of the equation by r, and we get r times s sub n equals a sub 1r plus a sub 1r squared plus a sub 1r cubed all the way down the line to a sub 1 r to the n. Well, what if we take that and subtract with the s sub n equation? What if we take the s sub n equation and do minus r times s sub n? Well, if we subtract those, we'll have the a sub 1, but notice that, like, you'll have all these terms that cancel out with each other. And you'll be left with a sub 1 minus a sub 1 times r to the n. So you have this term minus this term, if that happens. Because everything else in between will go to 0 when you subtract. So you can take that and clean it up a little bit and come up with a nice formula. You can factor out s sub n and get this. And you can factor out a sub 1 and get this. Then you can finally solve for s sub n by dividing both sides by 1 minus r. So when r is not equal to 1, there's your formula for finding the sum of the first n terms of a geometric sequence. Okay. So let's go back, way back to that first example that I hit in this video. So back to the gifts example. Person gets $50 on January 1st. Doubles each month. Then December 1st, they end up with $102,400. Our R in this case was 2, because you're doubling each month. Our N is 12. And what if we want to know what is the total amount of the gifts throughout the year? So when I first posed this question, we were dealing with the matter of the sequence and trying to find that last term in the sequence. Now we're trying to find out what's the sum of all the possible terms in that particular sequence. Well, we're basically trying to find the sum. Well, let me erase that thing there. So we're trying to find s sub 12. So we have a sub 1 was $50 times 1 minus 2 to the 12th power all over 1 minus 2. Because r is 2, n is 12. We're using our little formula up there. Okay, so let me see what I end up with. Okay, when I do the top, I end up with $50 times 40.97, and it's over, well, I actually end up with negative, let me see here, let me do this again. Sorry, I end up with negative 40.95. And it's over negative 1. So I'm going to end up with a positive answer. But then when I multiply, I end up with $204,750. So yeah, that ended up being negative 40.95 right there. Accidentally punched the wrong key in the calculator at first. But there you are. So that would be the grand total if you added up all the gifts you get from each month. Okay, what if they throw in that sigma again? Remember that? The Greek letter sigma, that means summation. I equals 1 to 8 in this case. This time we have 4 times 5 to the I power. So they're basically wanting you to figure out, like if you plugged in 1, 2, 3, 4, 5, 6, 7, 8, and then added up the results, what would you get? And you could sit there and you could find them. You could do 4 times 5 to the first, 4 times 5 squared, 4 times 5 cubed, 4 times 5 to the fourth, etc. until you got to 4 times 5 to the eighth, and then added up your results. Or you could use the fact that this is technically a geometric series. Your r is 5, because that's what keeps getting multiplied more and more as I increases from 1 to 8. Your r is 5. Your initial term would be 4 times 5 to the first, which is 20. And then your n is 8. So really, you're finding s sub 8. You can do 20 times 1 minus 5 to the 8th power all over 1 minus 5. So let me do that again. I'm not used to this calculator. All right, so do the whole thing on the top, divide by negative 4, and you end up with grand total 1,953,120. Pretty good sized numbers, so I'm kind of glad that we didn't sit there and actually find all the terms in the sequence and then try to add them up. That would have been kind of annoying. Okay, so that's fun with these finite series. What if we have an infinite series? Huh. I've been debating in my head whether to really say much about limit, but I think it's necessary. Most of you are probably heading to calculus later, so you're going to see limits quite a bit. But let me kind of briefly talk about what a limit means and then how it applies to if we're doing infinite geometric sequences and series. So let's say you have a geometric sequence like 2, 1, 1/2, 1/4, 1/8, 1/16, etc. And this is infinite because you see the dot, dot, dot means it keeps going on, and it can keep going on forever and ever. A sub 1 is 2. R is 1/2. Start with 2. Keep multiplying by 1/2 to get the next term. If we start looking at the sums, S sub 1 is 1. S sub 2, S sub 1 is 2, sorry. S sub 2 is 2 plus 1, which is 3. S sub 3 is 2 plus 1 plus 1/2, which is 3.5, or 3.5. S sub 4 is 2 plus 1 plus 1/2 plus 1/4, which gives you 3.75. S sub 5 is 2 plus 1 plus 1/2 plus 1/4 plus 1/8, which gives you 3.875, and so on. So S sub n never reaches 4. It starts to get closer and closer to it, but you keep adding these smaller fractions. So you keep taking another, like closing the distance by 1/2 basically, but you're never going to quite get there. So it never reaches 4, but it keeps getting closer. It's kind of like the idea where if you stand 10 feet from somebody, you could close the distance by 1/2 and now stand 5 feet. Then you could close the distance by 1/2 and now stand 2.5 feet. You could keep closing the distance 1/2. And if you ignore physical constraints, like your feet, or even if you could keep closing that distance by 1/2, just ignoring even things at the molecular and atomic levels, if you could keep going more by 1/2, you would never have to touch that person, but you could keep getting closer to them. So that value it keeps getting closer to is considered to be a limit. So the sequence converges to 4. Or we could say the limit as n approaches infinity, so as your n gets bigger and bigger, the limit of that sequence is 4. It won't, in this case, it won't actually reach 4, and it would never go past 4, but it keeps approaching 4 more and more. So the limit of S sub n as n increases without bound is 4. So in this case, the limit of 4 is the sum of the terms of that infinite geometric sequence. So what if you had a sequence that looked like this? 4 plus 4/5 plus 4/25, etc. Well, you see that it starts at 4. And then S sub 2, you add 4 and 4/5, you get what, 4.8. S sub 3, let's see here, I'm going to need to do a little math on my calculator. 4 divided by 25 plus 4.8, and I get 4.96. And I could keep going. Since it gets closer and closer to 5, it'll never actually reach 5, because you keep multiplying previous term by 1/5. So you're going to get these smaller and smaller fractions, but you're never going to quite close that gap all the way to 5. But you could still say it converges to 5. So you can say that the sum, or the answer in this infinite sequence, is 5. Okay, what if we want to try to generalize this a little more? What if we want to try to come up with some kind of a formula to help us to work with this? If you have something like 1 plus 1/3 plus 1/9 plus 1/27 plus etc. Well, let's say you're trying to find S sub n, and you're trying to use your formula. Okay, so like this one, a sub 1 is 1. Your r is 1/3 because each term can get multiplied by 1/3 to get the next term. Let me do brackets. But let's think about what's happening here. The 1 minus 1/3 on the bottom, that's no big deal. You end up with 2/3 there. Multiplying by 1 at top, that's not really a big deal either. But inside the brackets, we need, what's happening to the 1/3 to the n power is a big deal. As n gets bigger and bigger, what is happening to that? Let's think for a second. The limit as n goes to infinity of 1/3 to the n power equals what? So as you increasingly take 1/3 to powers, 1/3 to the first power is 1/3. 1/3 to the squared is 1/9. 1/3 cubed is 1/27. This keeps getting smaller and smaller and approaches 0. So when you take a fraction like 1/3 and raise it to the nth power, as your n gets bigger and bigger, your results get closer and closer to 0. So we can use this and translate it to finding, like, what if this was infinite? So what if we wanted to do the limit as n approaches infinity of S sub n? So that's going to be the limit as n approaches infinity of what we have going on here. Well, up top, you've got 1 minus 0. On the bottom, you still have 2/3. Because the numbers like 1 and 2/3, they're going to just approach themselves. They're going to be themselves still even when you go to infinity. It's the n that we're worried about. So you end up with 3/2. So thinking about this as an infinite sequence, the sum would end up being 3/2. All right, how about if we get a little more generic with this? Okay, so we have S sub n equals a sub 1 times 1 minus r to the n over 1 minus r. This r is not 1. If the absolute value of r is less than 1, so in other words, if r is some fraction, there, the proper fraction, then the limit as n goes to infinity of r to the n is 0. So the limit as n goes to infinity of S sub n is going to be a sub 1 times 1 minus 0 over 1 minus r. So it's going to be a sub 1 over 1 minus r. So rather than saying S sub n, let's say S sub infinity. S sub infinity equals a sub 1 over 1 minus r. As long as absolute value of r is less than 1. If you've got an absolute value of r greater than 1, the terms increase without bound. an absolute value. So no limit. So like if your r is 2 or 5, there's not going to be a limit like this as n goes to infinity. So if that happens, there's no sum. You can have a sequence where the terms keep, increasing without bound, as far as their absolute values are concerned, but you're not going to be able to find a final sum if this continues to infinity, because you're not going to approach a particular value. But if you have a proper fraction for your r, the absolute value of your r, then you've got this nice tidy little formula for finding that sum. Okay, let's do an example there. Let's say you're trying to do the sum of I equals 1 to infinity. You got 2/5, and then you got negative 1/3 to the I minus 1. Okay. So what do you got for a sub 1? Well, for a sub 1, 1 minus 1 is 0. That would be 2/5. A sub 1 is 2/5. And then your r is negative 1/3. The absolute value of negative 1/3 is 1/3, which is less than 1. Okay, so we can do this. We can say, well, if we want to find the infinite sum, we can use a sub 1 over 1 minus r. Let's see what that's going to get us. So we have 2/5 over basically 4/3. So 2/5 times 3/4. So we end up with 6/20, which reduces to 3/10. So if you started, coming up with all the terms in that infinite sequence, and start doing sums, you would see that the limit is 3/10. Okay, let's try another one. Let's say we have the sum of j equals 1 to infinity, so another infinite sum, of 0.9 to the j power. Okay, so a sub 1 would be 0.9. Also, your r is 0.9, because that's what you're multiplying by each time. You're trying to get a new one. So if we were trying to do this infinite sum, a sub 1, 0.9 over 1 minus 0.9. So 0.9 over 0.1, and that gives us 9. So there's that. All right. Okay, so one final example. Let's do an application property. Let's do an application thing. This one involves finding the future value of an annuity. A sequence of equal payments made after equal periods of time, such as car payments or house payments, is an annuity. If the payments are accumulated in an account with no withdrawals, the sum of the payments and interest on the payments is the future value of the annuity. All right, so annuity definition. Sequence of equal payments made after equal periods of time. And if you want to talk about the future value, that's the sum of the payments and interest. So like if you put all the payments and interest into an account and let it just sit there, the future value would be like at the end of a certain period of time, what is it worth? Now the formula for future value of annuity is S equals R bracket 1 plus I to the n minus 1 over I. So S is future value, R is payment at end of each period, I is the interest rate per period, and n is the number of periods. This is basically a version of compound interest formula worked with our geometric sequence formula. So it all comes together and creates this. If you'd like to see kind of how it comes about, check out your book. There's an example worked out. I'm just going to jump right into doing an example using the formula. Let's say a gentleman named Clayton deposited $3,500 at the end of each year. $3,500 deposited end of each year. And this is done for 6 years in an account paying 3% interest. And this interest is compounded annually. Okay, and we want to find the future value. Okay, so $3,500 is the payment that's being made. So the end of the first year, you drop $3,500 in there. Then the end of the second year, that $3,500 has earned interest, and then you're dropping another $3,500 in. Third year, the first deposit has earned 2 years of compound interest. Second deposit has earned 1 year of compound interest. Third deposit has not yet earned interest. And you keep doing this for 6 years. At the end of 6 years, that last deposit doesn't get a chance to earn any interest because you're depositing it at the end of the year. But all the previous deposits have started having compound interest stack up on them. And you could work this out the long way and take each one and figure out its compound interest. You know, you could think about the fact that, okay, the first $3,500 deposit is earning 3% interest, so you times by 1.03, but this is done 5 times. The second one gets to earn it 4 times. Third one gets to earn it 3 times. Fourth one gets to earn it twice. It's compound interest, so you're multiplying by that 1.03 each time. This one gets to earn it 1 time. And then the last one, the 6th year, doesn't earn any actual interest. So that's what's actually happening. If you want to go through and compute all that and put it in, you would get your result. Or you can just rely on your formula as kind of a shortcut way of doing this. You could say, well, I have $3,500, bracket 1 plus 0.03 raised to the n, which is 6, minus 1, all over 0.03. That'll get you the same kind of result. So let me pull out my handy dandy calculator here. 0.03 raised to the 6th power minus 1 divided by 0.03 and then times 3,500. And I get a whopping total of, I'll go and round as near cent, $22,639.43. So it got me the same result. So there you go. All right, you know what? I think that's enough fun with geometric sequence and series. If you have further questions, of course, never hesitate to reach out to me, but that's all I have for this video for now. We only have a couple more videos for my pre-calculus course. You get to look forward to talking about the binomial theorem next. I feel like that one's kind of fun. And then we're going to do a little discussion on mathematical induction. And that will actually, for this season, wrap up our pre-calculus course. So, going to be coming to an end soon, sniff, sniff. All right, well, thank you for joining me once again, and I will see you again soon, where we'll move past these sequences and series and talk about the binomial theorem.